Hi students. So today we are going to discuss about when you are placing a dipole in an external electric field, what is the force acting on the dipole and what is the torque experienced by the dipole, and then what is the potential energy of a dipole in an external electric field. So first I am going to start with what is a dipole. So dipole is nothing but two equal and opposite charges separated by a very small distance, right? So first I am going to start with, I have a dipole here. First I have a I have a dipole positive charge here, I have a negative charge here, right? So separation between these two charges is with positive q, this is negative q. So the separation between them is going to be 2a. The dipole moment in this direction. So dipole moment is always from negative to positive direction. So first I am going to start with, if you apply the external electric field now. So now this is the direction of the external electric field E, which means this is my uniform external electric field. So this is some positive charge be here, some negative charge be here. My electric field lines always flow from positive to negative. So because of this positive charge, what's happening? Because of this positive charge experiences the repulsive force. This charge tends to move in this direction. F is equals to Q into E. So because of this positive charge, because of this applied external electric field, the negative charge is attracted by this. So this force acting in this direction is my F is equals to minus Q into E. So one force acting in this direction, one force acting in this direction. So I am going to write the net force. One is plus Q into E, the other one is plus of minus Q into E. So it's going to be 0. So my F net is going to be 0. The net force acting on this electric dipole is going to be 0 because two antiparallel force acting simultaneously. But my net torque is not going to be 0 because here my two forces equal magnitude exactly in the opposite direction. That's why the net force is going to be 0. But the torque experienced by this charge, because this charge it tends to rotate this direction, this torque it tends to rotate in this direction. The torque it's not going to be 0 because of this is going to be ripple. This tends to move in this direction, this tends to move in this direction. So this is my torque experienced by this charge and this is the torque experienced by this charge. So both the torques in the same direction, it's in the clockwise direction. So the net torque experienced by this dipole is not going to be 0. So if you want to write my torque, I can simply write my net torque experienced by the dipole tau equals to R cross F, force into perpendicular distance. So I can simply write R cross F. So R is nothing but the perpendicular distance. So the perpendicular distance in this case, I can simply write here. So I can explain here. This is my positive charge. This is the negative charge. So this is a straight line which makes an angle theta. So the projection of this in this direction is going to be one force against in this direction, one force acting in this direction, negative charge F into equals to minus Q is going to be F is equals to plus Q, which makes an angle theta. So the perpendicular distance I can simply write 2a. So this is going to be the perpendicular distance. This is going to be a cos theta, it's going to be a sin theta. Then I can simply write my perpendicular distance. Okay, so this is my applied force, this is my perpendicular distance. Then I write it's going to be a sin theta. I have to write 2 into a sin theta because the distance from these two charges is going to be 2a. So 2a sin theta into F is equal to Q into E. Then I may write 2 into a Q E sin theta. So what is my dipole moment? My dipole moment is nothing but Q into 2a. So I can simply write my electric dipole moment P into E sin theta is my torque. So the net torque experienced by the dipole is going to be PE sin theta, right? So I can simply write in the vector notation tau is equals to P vector cross E vector. So this is my PE sin theta is nothing but P cross E. So this is my electric dipole moment. This is applied external electric field. So because of this applied external electric field, the dipole experiences the torque, which means some work is done by the external electric field. So according to your work energy theorem, so whatever the work done here, this work done stored as the energy of the system. So in the 11th standard, you studied about the work energy theorem. So what are the work we are doing against some force. So this work done stored as the energy of the system. In this case, this is the work done by the external electric field. So this work done stored as the electrostatic potential energy of the system. So first I am going to start with the potential energy. So if you want to find my potential energy, we should know the work done. So I can simply write the work done here. So the work done to move from initial position to final position. So I am going to use the integration. I am going to move my particle from initial position is going to be theta 1, the final position is going to be theta 2. So initial position and this is my final position. Tau is a function of theta into d theta. What is this d theta? It's a very small distance. Okay, so if once I integrate, this d theta will get cancelled. This will goes off. So if I substitute this value here, then I can simply write integration of theta 1 to theta 2. So P into E sin theta d theta. So if I integrate this, I am getting the value of minus of PE cos theta. So upper limit theta 2, lower limit theta 1. So I need this space. Let's erase this part. So my work done I can simply write. So minus P, I'll just bring it out. Cos theta 2 minus cos theta 1, right? So I'm just write upper limit minus lower limit. So if I bring this minus sign inside, then I can simply write my PE cos theta 1 minus cos theta 2. So this is the work done by the external electric field. So this work done stores as the electrostatic potential energy of the system. So this is nothing but the potential energy of a dipole in an external electric field. So this is nothing but UE. Okay. So now I am going to fix my initial conditions. Sir, why I am going to fix my initial conditions? Because my torque is not only depending upon P and not only depending upon E, it's also depending upon angle theta. If I apply my electric field which is parallel to the dipole moment, my net torque is going to be 0. If my net torque is going to be 0, my work done is also going to be 0. So what I am going to do here, I am going to fix my initial conditions. When my torque is going to be maximum? When theta is going to be 90 degree. So when my initial condition is fixed. So what I am going to do here for special case, I am going to fix my theta 1 is going to be pi by 2. Why we are going to fix my theta 1 is pi by 2? Because then only this dipole experience the maximum torque. Then only we can find the work done. If I apply my electric field along this direction, what's happening? My net torque is going to be 0. If net torque is 0, there is no work done. Then the potential energy for dipole in an external electric field also 0. So I have to apply my force perpendicular to the dipole moment. So I can simply write theta 1 equal to pi by 2, theta 2 equals to, I can simply take my final displacement as my theta. So if I substitute theta 1 and theta 2 value here, my UE will become PE cos pi by 2 minus cos theta. So this term is going to be 0. So my potential energy E equals to minus PE cos theta. So this is my final expression. This is the energy, this is a potential energy of the dipole in an external electric field. So next we will fix the theta value. So I can simply write, so case 1. If I write theta equal to 0, which means the angle between the external electric field and the dipole moment is 0. What's happening? My potential energy equals to minus P into E. If my potential energy is negative, the system is in most stable state. Simple, I'll explain here. So what's happening here? So this is the direction of electric field. So this starts from positive and this starts from the end with negative. So my dipole moment also should be parallel with this. So this is my dipole moment. But this should be negative charge and this should be the positive charge, right? This should be a positive charge, which means this negative charge is attracted by this charge and this positive charge is attracted by this charge. Then the system is in the most stable state. So my theta is nothing. When theta is equal to 0, the system is in most stable position. This is a very, very important question for the not only for CBSE exam, it's also important for the NEET as well as the JEE questions. So when theta is equal to 0, the dipole is in most stable state. When my potential is negative, the system is in the most stable state. So I can simply write most stable position. Most stable position when theta is equal to 0. Sir, what's happening when my theta is going to be anti-parallel? So in this case, if we put 90 degree, what's happening? My potential energy is going to be 0. So I should not take my theta is equal to 90 degree. So I can simply write here when my case 2, when theta equals to pi by 2. Actually, this is for your final position. Okay? When my theta is equal to pi, oh, not pi by 2. Pi by 2. If I put pi by 2, cos 90 is going to be 0. So I can simply write cos pi. If I write cos pi, my UE equals to plus P into E. So this is called most unstable position. How? I'll explain. So this is the direction of electric field. My dipole moment exactly in the opposite direction. So this is positive, this is negative for the electric field. And then for dipole moment, I can simply write this is going to be negative, this is going to be positive. So this positive charge which will repel this positive charge which will repel this. So this may move either this direction or this may move either this direction. So my dipole now is in the most unstable position. So this is called stable equilibrium. This is called unstable equilibrium. So when my theta is equals to pi, then this is called unstable position or unstable equilibrium. So whenever you are placing an electric dipole in an external electric field, it experiences a torque. When it is experiencing a torque, the net force is going to be, first initially start with the net force experienced with the dipole is going to be 0, since both the forces are acting in the opposite direction, anti-parallel. So if I add these two vectors, it's going to be 0. But in the case of torque, both are in the same direction. So we have a finite torque. So if there is a torque, we can find the work done. Because of the torque, the system starts rotating, dipole must starts rotating. Because of this rotation, what's happening? There will be some work done by the external electric field. So we are able to find the final potential energy. So we just then fix the value of theta 1 equal to pi by 2 and theta 2 equal to theta. So after finishing this, we are able to get this relation UE equals to minus PE cos theta. So when your theta is equal to 0, this is called most stable state or stable equilibrium position. And then when theta is equal to pi, so this is called when my potential energy is positive, the system is in unstable state or unstable equilibrium. So these two conditions are very, very important for the exam point of view and the NEET exam or and then J exams also. So I just stop at this point. So if you like this video, subscribe our channel for the more content and share with your friends, and we'll meet in the next class. Thanks for watching.